Hi, this is the lecture recording for the section 7.3. So let me see. Okay. So here's the setup. We have x and y. Let's write it as a z, and y is subject to missingness. And we have an estimating function, estimating equation that defines the parameter. And the true response probability follows the parametric model. So we have a this is unknown parameter, but this function is known, right? So then if we can somehow obtain a root and constant estimator of the parameter, then we can plug in 2 pi to obtain pi I hat and use the inverse of it as a weight and solve this equation. So basically in the previously we have a WCC estimator, and now the weight is estimated. Okay. And then there are several research questions. So first question is how to estimate, right? How to estimate a parameter. And we can use maximum likelihood approach or estimating equation approach and things like that. And then second question is once we plug in pi I hat and solve it for theta, and then what is the solution? So what is the property, statistical property of the PS estimator? So, and then how to improve the efficiency? So that's another question, but we'll cover this next class, not today. So okay, the first one is about a maximum likely estimation. So then the observation we have, we observe xi, right? And yi, and delta I, and yi only when delta equal to 1. So that's our data, right? And then the joint density can be written as something like this. So we have a marginal density of x, and so x is always observed, so you don't have to worry about that. And then you have a y given x, and then probability delta equal to 1 given xi and yi, right? So that's basically take care of the joint part with the delta equal to 1. And delta equal to 0 case, we don't observe y, so we cannot really write it. We need to integrate out over y, right? And this one is actually the conditional probability of the delta equal to 0. And then we take the integration. And so then now so this is actually marginal density. So marginal density of the data. And then use that to construct the likelihood function, which is the observed likelihood function, right? And then we take the log, then we get, and basically then this is just a constant. It has nothing to do with the phi. So they can just disappear. So you don't really have to worry about, because they are essentially constant in terms of phi. But then this delta I times log pi, right? Log pi plus 1 minus delta, and then this guy is actually comes here. So log of 1 minus pi tilde, and then pi tilde. So basically this is the integration. It is a probability of delta equal to 1 given x, which is 1 minus pi tilde xi. Okay. This one. So this one. Okay. And then the pi tilde is the so this is delta equal to 1 given xi x, right? And which is, So you have a property delta equal to 1 given x and y, and then you average, take the conditional expectation over y. So that is the marginal property of response. Okay, so that's the general case. That's for general case. And now for missing a random, we have some simplification, because then response mechanism doesn't really depends on y, right? So this doesn't depend on y. So you can go outside the integration, and then basically the integration of the density function is equal to 1. So then you have a simplification. So that's basically log likelihood of the phi on the missing and random. Okay, so this, then you there's really no integration over, right? Here you have a some conditional taking the conditional expectation, but here you don't have to, right? I mean, because you just observe. So you observe xi and delta I, right? 1 to 1, no missing. So then you can just use it. So then in this case, the MLE is very easy to compute, and then you can just obtain score equation to solve for phi hat, to obtain phi hat, and then plug in. So obtain phi hat and plug in here, right? And then solve for zeta. So you can do it kind of a two-step procedure. So this is basically joint estimating equation, and then you have you can use the sandwich formula to obtain variance estimation, compute the variance. So now here's a one interesting result. So we have so for this guy, right, the PS. So let's write it as a U1, to make it more general. And then if this one has a zero expectation, okay, and so okay, so here we may say that this is the parameter of interest. Zeta is a parameter of interest, and phi is a nuisance parameter, right? And then the partial derivative with respect to nuisance parameter turns out to be, I mean, so basically you have two parameters, and the partial derivative with respect to the another parameter turns out to be the covariance of the original estimating function and the score function derived for the parameter here, for this parameter. So that is some, we need to prove, prove this, but one in special case is if u equal to s. If we put u equal to s, the score function itself is already mean zero, right? And then the partial, then the result 3 leads to this result, which is actually, we already see this. This is what we called it, Bartlett identity. Actually, second order. First order is about the score equation, right? I mean, score function is zero, expectation is zero. So, okay, let's prove it. Notice that U1 is a function of two random variables, Z and Y. Sorry, Z and delta. So U1 is a function, U1 as a function of parameter, so estimating function, right? So you have a two parameter, but this is actually a function of two random variable, C and delta. And so when we say expectation, so it means expectation. So So it means expectation means integration, right? So it means integration over the joint density of the Z and delta. So what is the, so then you have a marginal density of Z and then conditional density of the delta equal 1 given Z. But the parameter, we are only care about parameter. So parameter phi, so let's write it. Okay, dz and d delta, whatever. Oops. So actually this is not really correct. Delta is a random variable. So we can just write it as delta given z. And then phi, okay? And then d, z, and delta. Okay, something like that. And now what we are interested in doing is the computing so this is 0, right? This is 0. And then by assumption. And then we want to apply partial derivative. So partial, if you do partial derivative, this is 0 because we are taking the partial derivative of 0 function. And then let's investigate what it is, what this guy is. So notice that we only care about phi. So phi is here and here, 2 places. So that means we want to apply phi here first. Right? Apply phi, and then everything else is the same. Oops. Plus u1 zeta and phi, z and delta, fz, and then phi. Okay. Then the first one is just the computing the conditional expectation over the partial derivative. That's it, right? I mean, yeah, so we don't really have to have this. Okay. Second one, we need to add one more step. So what is this? This is, we have the same, we use this technique several times as phi times, so partial derivative of the density is a score times density. Okay. So if you use that, then the second expectation is just the product of 2 expectations. So that means what? This is 0. And this guy is equal to the covariance of U1 and S, because the expectation of U1 is 0. So then that basically proves the result, right? 3. Because you have a minus. So this is add sum of the 2 is equal to 0, then 1 is the minus negative of the other, which is basically this result. Lemma. Okay. So that is a one lemma that we're going to use to apply the sandwich formula. So now let's move on to sandwich formula. So basically, this is our equation, right? This is our equation. So we have a parameter of interest theta and nuisance parameter, and this nuisance parameter has an equation. So if you just view this as a joint estimating equation, then you can just do so you can just write it as a single equation. Single equation of the joint equation of the, so as a vector. So U is a vector that has a U1 and S, something like that. Then sandwich formula applies. So then basically sandwich formula, you have a sandwich part, bread part is partial derivative, and the ham part is a variance covariance matrix, right? Of this equation. So that's this. And now we need to first compute the inverse of A. But let's if you look at this carefully, we have some nice result. The first one is that the scope function S itself is free of theta, so that this component is equal to 0. Okay, and so then this is A basically becomes a upper triangle matrix or something like that. So inverse is relatively easy to compute. Okay, so you can easily check whether, so A is what? A is A11, A12, A11, A12, 0, A22. And then if you use this one, then you can easily check that the matrix, so this matrix times, A11 I minus A11 inverse, A12, A22 inverse, 0, A22 inverse is equal to I0, 0, I. Okay. So you can check that, and that's actually fairly easy algebra. And so that's fine. And then after that, we basically want to A inverse B A inverse, right? Prime. And so now you have A inverse is A11 inverse minus A12 minus A12. So it's a bunch of matrix algebra basically. A22. Okay. And then you have a B11, B12. So you cannot really simplify the inside 21, B22, right? And then you have a transpose, so which is now you have A22 inverse A21 A we don't have A21. So well, yeah, right. We just have a A1 to prime. Okay. Prime A22 A12 inverse, something like that. Okay. Yeah, that's a little bit 0. Okay. And then simplify. Then you have a 2x2 matrix as right? A black diagonal matrix. But what you care is so this one will actually gives the variance covariance matrix of the theta hat PS and phi hat. But what you care is only the upper part. So then you can actually a little bit simplify, because then all you have to do is basically what you really care about is the matrix algebra of this one times this one times this one. Okay, actually we lost one A2 2 inverse here. So, but nonetheless, we have this. Okay, because what you end of the day, what you care about is this guy, the upper, right? This guy, upper left part of the matrix. So then that actually can be written as something like this. So something like this. And then now we have a further simplification. So good news. The good news is lemma 7.3. So the lemma 7.3 says that you have basically this 3, right? So then what's the relationship? So what this means in the context of this matrix? Well, basically this guy, so lemma 7.3, okay, so lemma 7.3 implies this guy is equal to this guy. So this is equal. And also this guy is equal. Equal. Lemma. So that means A12 is equal to B12. A22 is equal to B22. Okay. That's very good news. So let's move on. So that basically means A12 is equal to B12 and B22 is equal to A22. So then you actually have a further simplification, which is basically, so this guy and this guy is equal. This guy and this guy is equal, essentially. And so end of the day, you have this guy and this guy cancel. So you actually have a lot of simplification so that this is what you get. Because you have the same thing, minus, minus, and plus. Same thing. So you have a, okay. So that is the very nice result, right? So basically what it says is that, so what this means. So you have a variance of U1 minus covariance U1 and S, variance S inverse and variance S in U1, which is actually here. No, we don't have a, so let me write it here. So So 4 is that variance of zeta hat PS is approximately equal to A11. A11 is what? A11 is basically expectation of the partial derivative of U1 inverse. And then variance of U, which, right, this is U1, U1, variance of U1 with the known pi, with the known phi, basically. U1, and then covariance S, oops, okay. So let me write it. Yeah, you have a something P11 minus P12, P22 inverse P21, right? And then same thing here. So then this guy, what this guy is variance of U1, U hat 1 minus covariance of the U hat 1 S, and then variance S inverse, and then covariance of S and U hat 1, something like that. Okay. So that is equation 4. And then this guy, original weight with the known, right, with the known phi 0 is actually, in our theory, we have that is basically P11 inside, sandwich formula with P11. So which one is smaller? So this guy is a A11 inverse B11 A11 inverse. This guy is A11 minus B11 minus B12 B22 B21, right? Inverse, something like that. A11 inverse. So see, this guy is actually positive, non-negative definite, right? This is non-negative definite matrix. So that means you have a subtraction here going on, subtraction of the non-negative thing going on. So you get this inequality. So what is the interpretation? What is the intuition? If you know true parameter, and this is the you estimate, right? This one is using the true parameter. So we can construct two versions. One is done using the true parameter. The other one is using the estimated one. But turns out that using the estimated one is actually better. So that is kind of uh, 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 paradoxical problem, because usually in the case of the usually in this user estimation problem, uh, the variance with the estimate parameter is actually reduce the right estimated losses parameter usually reduces the variance. No, increase the variance, reduce the efficiency. But here actually the other way. So that is interesting. And okay, so here's some high level interpretation. So how do you interpret this one, this result? So this is a little bit mathematical. So we have in the Hilbert space. So we are now talking about thinking about some sort of random space of random variables with a mean 0. Okay, and then finite second moment, and then how can we define projection? So projection of y on x satisfies. So you have a space here, space of the for example linear space of random variable x. Okay, that means you adjusted this one, right? So this x can be actually vector random variable, or I mean so then basically the projection means two things. First one is the projection should belong to the space, right? Also, to be a good projection, it should be orthogonal, right? Orthogonal too. So that means orthogonality means that this residual, so this is y, and this is the projection here, right? Projection of y given y at x. So this is the vector. That vector should be orthogonal to all element. Okay. So that is the definition of the projection. And then in the linear space, actually we can use some sort of the, so we are basically we solve this kind of right, and x, right? If you solve this, because it's orthogonal, right? So residual should be orthogonal in terms of the norm. So the norm here is the cross, I mean covariance. Okay, so then if you solve this, and this is basically linear, so ax. So then you can easily see that this is actually this. So your optimal this is a star, right? The solution that satisfies this equation should be this one. Okay. And also, and then another interesting part is that you can think of the orthogonal space. orthogonal complement. So your space is the all the element. So you can, so this is the orthogonal complement, and then turns out that if you project on the orthogonal complement space, you can improve the efficiency. So basically, if you define in this case, okay, so you have of course you have a zero. I mean, uh, same expectation, and then here basically this is what, this is covariance, this one, right? Covariance y given x, y and x, and the variance x inverse and x. So this guy is actually said has the, so this guy y minus, so this is the kind of a residual, but as long as you have a zero expectation here, the expectation of the, so this guy becomes a more like optimal estimator y star, in the sense that it has the same mean as same expectation of y, original y, but with a smaller variance, because your variance is actually so this is the variance of the y hat star. Okay, so the projection onto the orthogonal space will always improve the efficiency. So later we will use a score. So you have a score function of the nuisance parameter, and then you project the original estimator to the orthogonal complement space of the score function. So that is what we are doing here essentially. Well, so the remark is okay. So here's a remark. So if you look at this, so you have something like, okay, yeah, okay, yeah, it can be anything, right? I mean, so actually we have this is not exactly, because let me right, back up. So we start with defining, you had PS, right? Zeta. So that is actually serving something like this: delta I pi I hat yi minus zeta. So if you solve, so this is the definition, and then if you solve this for 0, then you can get what, zeta hat PS is a kind of ratio, delta I minus pi I hat delta I yi minus pi I hat, right? Okay, but whatever it is actually function of phi hat anyway, right? So then we can remember we view, so we in the imputation, right? In the imputation linearization, we have a beta hat, right? In the regression imputation, and so we just do linearization. So basically we have a different nuisance parameter here, because we have a phi hat obtained from s equal s phi equal to 0, right? To obtain phi hat. So that actually is this phi hat. Okay. So then you can basically, once you get this, so then your phi hat is, you can use tail expansion, phi 0, and then phi something like that, approximately. Okay, and then what? And then we also have a equation. So 0 equal S hat phi hat, right? So S hat, I mean, if you write it this way, P0 plus, so actually we have a prime. Okay, I mean, we have a approximately. So combine the two, and then combine the two. And by the way, if we know the true, right, true parameter, we call it a WCC. So that's why we use subscript here, but it's not really a big issue. So anyway, if you combine, right, so you can basically combine these two, then you get this 7 linearization. Okay, so then this is linearization. And now let's take a look at what this is. So basically we have, right, this is the usual approximation, where actually this is approximation. So basically you can, is information is a variance. So this information is a variance of the scope function, right? So you can plug into as a variance of scope function. And then partial derivative is what? Is a, so this guy, if you remember u function, right? UPS partial derivative is a negative equals minus is a covariance of the U and S, right? So that's here. So basically, end of the day, we get, uh, so this guy is a negative variance of S. This guy is a, this guy is a negative of covariance of the theta hat PS W times, I mean, covariance. Should, okay, variance of S. So first term is covariance of theta hat W S. Second term is variance of S. So you get something like this, which is actually form of the projection, right? If you remember, we did the form of the projection is this form. So now this X is a scope function. Then you end up, so this one is a set type PS. So set type W, right? Set type W, and then this one is a score. Then basically this equation, the expression here is actually same as 7. No, I mean this form. So the linearization shows that we actually have this projection. So that's why we get efficiency gain, something like that. So that that's a little bit high level result theory, and but let me move on to variance estimation and discuss it further. So on the MAR, log likelihood, okay. On the MAR, phi is I V plus 1 minus delta I log 1 minus pi phi, right? So then we let's take a partial. So take a differentiation. Then delta I. So let me do it in the next page. So okay, let's do it again. Phi delta I log pi I phi plus log 1 minus pi I phi, right? And then pi I phi phi pi I, right? Phi plus 1 minus delta I, and then 1 minus pi I phi, and then you have a minus. So then you can actually have some simplification, I guess. So we can basically use pi I 1 minus pi I here, and then delta I 1 minus pi I minus 1 minus delta I pi I, right? Yeah, so a bunch of algebra, but and then hopefully we can get some simplification, which is what we get. So delta I minus pi I, and then delta pi 1 minus pi I, and then so that is our score function, score equation. I mean, which is this one. So we can write it dot pi as the partial derivative of pi. So another way, I mean, this is one way, right? You can write this way. It's the same thing. So now let's try use the variance. We already have a form, which is the B11, B12, right? So that already, that we have that already. The only thing is how to compute the covariance. So the covariance, okay, is basically, yeah. So we use, okay. Yeah, we use using for. So using for here, right? So A11, right? P11, P12 minus P12, P21 inverse, P21. Then, okay. So let's do one by one. By the way, P11, let's remember, try to remember what P11. So yeah, so this guy, right? So we're gonna use that. So P11, P12, P21, P22 should be variance of U1, variance of U1, S variance of covariance of this is covariance basically. S and U1, I mean, and then variance of S, right? Okay. And now, what is U1, by the way? U1 is, let's see, normalize. So U1 is what? Delta I, pi I, right? With a known parameter. And then yi minus phi, etc. So that is U1. So variance of U1, remember, I think this is essentially WCC estimator. So if you remember, the variance of U1 is 1 over n square, something like that, 1 over pi I yi minus theta. I think this is what we derived in the last class, in the class last time, so that variance had 1, so which is B11. So B11 hat should be delta I pi I square yi minus theta hat PS square. So that is this one, right? So I mean, this is U, basically you theta Z. Okay. Similarly, covariance, what is the covariance U1? So covariance of U1 S is a covariance of the, so let's write it this way. So delta I pi I minus U, right? UI, okay. And then S, you can write this way, H. So that way you can write it as something like delta I pi I minus 1 HI. Okay. So this is actually nice form because conditionally zero expectation. So then the only randomness is to 2 delta. You can, so end of the day you get something like pi I square pi I 1 minus pi I, and then UI HI prime. I mean, there's some vector, I mean, S, right? It is, so this is, so that is basically, and then you estimate, so this is P11, P12. So P12 hat should be delta I 1 minus pi I square UI HI prime, which is this one. So is it really the same? Well, yes, because you have a pi I hat, then 1 minus pi I hat divided by pi I square is this one. Okay. And then last thing, one more thing to compute this variance of the S. So remember delta I pi I minus 1 HI. So then variance. So then we can write it same thing, pi I 1 minus pi I square HI prime. And then so that you can get estimator delta I 1 minus pi I square HI prime. Okay, which is basically this one. So that take care of the variance estimation. Okay, so now we have additional material, another approach. So I'm gonna briefly cover these two. So well, so previously, so far, we just consider maximum likely estimation for estimating phi, right? So how to estimate phi, we can use maximum likely estimation. One disadvantage of maximum likely estimation is that you don't really satisfy this. So maximum likely estimation satisfies delta I minus pi I hat equal to 0. So it satisfies this, not this. So remember, MLE supposed to be best for estimating the parameter. In this case, for phi. So MLE of phi should minimize the variance of phi hat. But this is nuisance parameter. We are not really interested in maximizing the efficiency of phi itself. Rather, we are more interested in maximizing the efficiency of theta, which could be different story. So then turns out that MLE doesn't necessarily give us the best estimate. For example, suppose y is exactly equal to 1. Y is all equal to 1. Okay. If you use MLE and compute, then you have a randomness. So then you have a variability. Even if you know y itself is no variance. That's then very weird, right? So then naturally we probably want to impose some normalizing constant. So anyway, so this is more generally you can think of using this one as an equation, estimate equation for parameter phi. And so then let's write it as a generally. So that means you suppose you use this kind of one as an estimator, and pi I hat, right? Delta I bi equal to sample mean of b bar. So if you choose b close to y, so for example, linear function in the basis function of the regression model, something like that, then this should be a good estimation, right? For not necessarily for phi, but for estimation of a set. So that is the basic idea. So as long as the PS model is correct and the solution exists uniquely, the solution to 10 should lead to constant estimator, because the expectation of this guy is 0, right? Under the correct model. And so then how to estimate the variance? Well, you can work out. So maybe this is good for homework. So you can work out the same algebra that I did here, right? I did all this algebra here already. So maybe no, I thought I did something like this. So well, we still have time. So let's do that. So okay, how can I show this? Well, before I show it, okay, before I prove this one is interesting, because this is basically you have some kind of a regression prediction, and then you have a regression residual, and delta I divided by pi I, which is a very similar thing to what we did for regression imputation, right? But this is not really exactly the same regression. Rather, we have a so B, you can view it as some kind of a basis function for the regression model, but you don't really get a B prime. Rather, you have H prime, which is this guy. So this is more like a instrumental variable regression. I don't know whether you guys heard about X prime. So X prime X inverse x prime y is regression, right? OLS, beta hat OLS. But z prime x inverse z prime y is the instrument variable regression. So basically, this is kind of doing here. So you have this is still x serves the role of x, but this one serves the role of z in this case. So this is a little bit different regression, but the overall form itself has the same flavor, right? So let's see how we can show that. So remember, it's the same story. So beta zeta hat PS is phi is a 1 over n delta I pi I phi hat yi. Okay. So and then you linearize. So you take the Taylor expansion plus take the partial derivative, which is, so if you look at the partial derivative, then you have the same thing here, but you have a negative because you have denominator. So you have a negative over the delta I divided by pi I phi 0 squared yi. And then what? Then you have a pi I. So and then you have a phi round the phi and round the pi I. Okay. And then phi hat minus phi 0. Okay. And then what is this then? That is basically we should make use of the equation, right? So remember you had phi hat equal to 0 is a 1 over n delta I pi I phi hat pi 0, right? So we are going to do the same Taylor expansion. So we're gonna do Taylor expansion of the 1 over n delta I pi I phi 0 minus 1 pi, right? Plus partial derivative. So which is same thing. You have a 1 over n summation I equal to 1 to n delta I divided by minus square because you have denominator differentiation. So p0 squared, and then same thing pi. So you have up here pi times delta pi I p I prime phi hat as phi0, right? So which is 0. So that means you can actually, if you combine, so we have two results, so 1 and 2. So we combine these two results, you end up getting zeta hat ps phi hat equal to zeta hat w. I mean, no, we can write it using the true pi, right? I mean, true phi. So let's write it as a delta I pi I yi. And then you have a, so this guy, you can write it basically. This looks a little bit ugly, but this guy and this guy, because you're gonna do inverse, so that will be combined. So you have a, so let's say 1 2, okay, and so you have a 1 here, and then 2 inverse, okay, times 1 over n. Let's write it 1 over n equal to 1 to n delta I pi I minus 1 pi. Okay, so this guy, the whole thing is actually can be written as, so what, so this, okay, is actually gamma hat gamma prime, this guy. So because because what's going on, so basically, yeah, this guy is a vector, and this guy we wrote it as a pi 1 minus, so h times, so this is h I prime times 1 minus pi I. Okay, here this guy is h I prime 1 minus pi I. Okay, so then you get basically this guy. You can check. So then you have a minus here, and so you can actually minus is applied. So let me simplify it further. So basically you have a, so you combine these two, then you have 1 over n I equal to 1 to n, and then gamma prime pi plus delta I minus yi minus gamma prime pi. Okay, so that is exactly what we want to show. And then because of that we can okay, because of that we can we established, what's going on. Okay, so that basically we proved this. Okay, and then you use this one as a kind of a influence function for variance estimation. Okay, I think that's all for today, and we'll continue next week. See you next week.